Hello and welcome to the third lecture of Advanced Functional Materials Part 2 of the Advanced Materials Chemistry course. Hello and welcome to the third lecture of Advanced Functional Materials Part 2 of the course Advanced Material Chemistry. So let us summarize what we studied in last lecture. Metal, semiconductor and insulators. Then we studied the difference of direct and indirect semiconductors. We also saw the difference between intrinsic and extrinsic semiconductors. Then we saw donor and acceptors. So donor are basically those impurities which donates electrons, and acceptors are impurities which take electrons from the system. Then we saw non-degenerate and degenerate semiconductors. When we say non-degenerate means the doping is low, and for degenerate the doping is very high. Then a different carrier transport mechanism we saw in brief. Then we see PN type semiconductors. What are P-type semiconductors? What are N-type semiconductors? And then we saw when we join them together and form a PN junction, what happens. This actually is useful in solar cells also. So we will see once again the PN junction today. Then generation, recombination and lifetime of carriers, how the carriers are generated, how they recombine, and the lifetime. Lifetime is how much time they survive in the before they recombine back. Then we saw some metal semiconductor contact, basically Schottky contact, and then we saw what are different semiconductor devices building blocks. Basically, there are four devices building blocks. One is metal semiconductor contact. There is PN junction, and third one is the heterojunctions, where two or more semiconductors are joined together having different band gaps, and then metal oxide semiconductor. So today now we will see the solar photovoltaics. So what is the source of energy which we receive from sun? We consider sun as a hot object of having 5800 Kelvin temperature. That is the temperature of outer core. And if any body is at any temperature, it emits radiation. So since it is at very high temperature, it is going to emit the black body radiation. So whatever black body radiation it emits, it comes to us, and it spreads actually in all the directions, and some part reaches at Earth also. So if we consider sun, then every second it emits 4 into 10 to the power 20 joule per second energy. And what is the source of this energy? From where this energy is coming inside the sun? There are continuous fusion reaction. These two reactions are taking place inside the sun. And because of this nuclear fusion reactions, the energy is generated, and that energy is transmitted. So out of this energy, approximately 1,73,000 terawatt heats the earth every day. And this energy is more than 10,000 times of the total world's energy requirement. So even if we can tap about 0.1% of this energy, that should be more than sufficient for our energy requirements. This is the typical solar spectrum which is received at the Earth. Now, if you see this curve, this is actually a black body curve at for any body which is actually at 5,800 Kelvin. So this is the outer part is the black body radiation of a body which is at 5,800 Kelvin and emitting this radiation. So this yellow part, what you see is the spectrum which is at the outside of the atmosphere. So you see this is matching very close to the black body spectrum of 5,800 Kelvin. Now, as soon as it enters inside the atmosphere, what happens? There are several gas molecules. They absorb, they excite vibrational levels. So then some part of this spectrum is absorbed. So what we receive at Earth is actually this, which is the you can say the red part. So if we measure the spectrum at just outside the atmosphere of Earth, the total energy is approximately 1,353 watt per meter square. And so this part, so if you consider this energy, so imagine it's a very high energy. In 1 meter by 1 meter area, you are getting about 1.3 kilowatt. When we come at the Earth, even after absorption of many of these things, many of these, you can say, by many of these molecules, still we receive nearly 1 kilowatt per meter square. So this is at AM1. What are these AM1, AM0? We'll see in the next slide. So AM represents air mass. What is air mass? Air mass, it is actually refers to the mass of air with respect to the vertical height of atmosphere that light has to travel before reaching the ground. So suppose this is the vertical height. So this is the atmosphere. This is Earth. This is atmosphere. This is sun. So when sun is here, you see sun is at here at zenith, then you suppose it travels x distance, and when sun is at some other place, it travels y distance. So this y divided by x, this is called as the air mass. Now, what is AM0? AM0 means this is exactly same as of the when sun is at zenith. In that case, both are same. So this energy is AM0 is when actually you are sitting here and there is absolutely no air mass is involved. So this is outside atmosphere. So as I said in earlier slide, it is nearly 135 milliwatt per centimeter square or 1,350 watt per meter square. AM1 is when sun is at zenith. So this is x, and so x by x is 1. And when that is this distance is 1.5 times to this distance, that is the called as AM 1.5, air mass 1.5. This is standard spectra of direct incident light, and its value is nearly 88.8 milliwatt per centimeter square. But what happens? There are some. This is the direct. When whatever radiation has been incident from sun directly, but you receive some indirect radiation also by scattering see this will be scattered by at several you can say molecules, so that will also come on the Earth. and so total will become nearly 1000 watt per milliwatt per centimeter square. So then it includes both direct and diffuse lights. Now, what are solar cells? So solar cells are those devices that takes light energy as input and convert it into electrical energy. So when when light is incident on the solar cell, it gives solar energy received on the earth. As I told earlier also, it is nearly 1000 watt per meter square or 100 milliwatt per centimeter square. So you can imagine how much energy we are receiving on the earth. It is very high, 1 kilowatt. So suppose you have a typical light or typical bulb which we are having in our houses is nearly the best in today's time. The LED, 50-watt LED gives a lot of light. So you can have 20 means 20 bulbs. You can illuminate 20 bulbs out of the energy which has been sent by sun in 1 meter by 1 meter square uh, area only, provided you convert it uh, completely into the electrical energy. So that is the reason why conversion efficiency of solar cell is very important. However, it is never 100%. Typically, between 5 to 25%. The commercial panels available are having efficiency of nearly 14%. That means if you are having a solar panel of nearly 1 meter by 1 meter area, it will provide you an power of suppose 14%, so it is 140 watt electrical power. Now, why do we require solar cells? Number one, it is renewable energy. It is clean and non-polluting. It is having high power to weight ratio, very easy installation and minimal maintenance. Once only to just do the clean part and of the contact there is a maintenance is required. Fuel costs or supply problems, have longer operational life, do not produce noise. Solar cells are very useful in remote locations like in sea, in space, where you cannot lay wires. Suppose you require power in space, what you will do? Best is the solar cells only. You cannot transmit the electricity from Earth to space, or in sea also, in deep sea, if you require power, then solar cells are very useful. It doesn't have any waste material. Now there are some issues also with the solar cells. What are these issues? Solar power cannot be obtained in night time, very obvious. Solar panels are relatively expensive. Energy to be stored in batteries, because whatever you get, first thing is that it depends on how much at present, how much intensity your power generated will change, because efficiency of the solar panel is fixed. So your current will change. And next thing is that it gives you DC power. So whatever we require in our domestic for the domestic purpose is AC. So first, this DC has to be stored inside batteries, and then it has to be converted back by using suitable inverters to AC, and then only it can be used. There is another problem, because there is a solar intensity fluctuations, so obviously there will be power fluctuations also, power generated by the solar panels. So that is the reason why these are stored in the batteries. There is no direct supply, and then after converting it back into AC, this is supplied to the domestic used in the domestic purpose. They need large area of land to produce more efficient power supply. So suppose this is only 1 meter by 1 meter is giving you 1 kilowatt. Suppose you want to install a capacity of 1 megawatt, then you can imagine how much area you require. So large area is one issue. Then another issue is with the tilt and alignment, because sun rise in the east and then it moves into the west. So the best or ideal situation should be when your solar panel should be facing sun all the times, but that is not possible. So this is also a big issue of alignment of the solar panels. That means you cannot use the entire sun. Cleaning issue in the large power plants, mostly it is dust, but removing the dust when you are having a plant for several kilometers area, then cleaning is also an issue. Now, let us see how the solar photovoltaic technology has evolved. So basically, the entire development can be divided into three different generations. The first generation is where the solar cells are wafer based. Then in the second generation, there are thin film based solar cells, and present generation, these are new emerging technologies which are basically organic and other devices. In the first generation, mainly monocrystalline silicon and gallium arsenide based solar cells were used, and these are the single crystals. The entire solar cell was fabricated out of the single crystals. Then there are another type of solar cells. These are polycrystalline solar cells, where actually the wafer used was not single crystal of silicon, but it was a polycrystalline silicon material. However, the size of the solar cell was same. In the second generation, which is actually thin film technology, amorphous silicon solar cells, cadmium telluride based solar cells, and CIGS solar cells. These comes under the second generation solar cells. And third generation solar cells, these are new and emerging technologies. See, these are not yet commercialized fully, but a lot of research are going on worldwide. These are organic solar cells, dye-sensitized solar cells. Though research on dye-sensitized solar cells is not at a very large scale now because of perovskite solar cells, emergence of perovskite solar cells, and quantum dot solar cells also. So these are also in research period only. So most of the third generation solar cells, they have not yet commercialized, but the first generation and second generation solar cells, they are commercialized, and the solar panels are available for both these kind of solar cells. So with this, let us see how a typical solar cell works. So yesterday we saw a PN junction. We saw what P type of material is and what N type of material is. So suppose this is a P type material, this is valence band, this is conduction band, and since it is P type material, so Fermi level is very close to the valence band. And you have N type material where the valence band and conduction band and the Fermi level is close to the N type, close to the conduction band. So now what happens when we join them together? We saw yesterday also. Now what happens when you fuse them together? You see there is a difference between Fermi level now. So Fermi level, there cannot be an you can say an abrupt change in these energies. So first thing is that Fermi level has to align. So for this alignment, what happens? The electron and holes moves from one side to another side, and then after some time, a thermal equilibrium is obtained, as we saw in yesterday's lecture or day before's lectures. So what happens after certain time, a built-in potential VB is established, and this Fermi level is uh, constant throughout the material, and so in between this portion you will have a gradient. And you can call this as a what we call this area, if you can recall, this is mostly depletion area. Now what happens when you join this and this, make a contact between p type and n type, then connect it with a load and it becomes your solar cell. What happens when a photon falls? Electron and hole pair are generated, as we saw yesterday. Because of this built-in potential, the electron is moving this side because of to minimize the energy. And similarly, the holes, first thing is they move at the junction, then they towards the depletion region, and then they move this side. And the electron moves through the external circuit. Now there is one thing, see, you have joined semiconductor with the metal. So what will happen? If you just join a semiconductor with the metal, a Schottky contact will be made. So now basically you will be having two back-to-back diodes. So ideally there will not be any current, because now you have two back-to-back diodes connected to each other, so there will not be any current. So there is a special techniques to make these junction and ohmic junctions. So the junction has to be made ohmic. It is not like that you just join a metal with a semiconductor and you will start getting current. So this was how a solar cell works. Now let us see what are some important parameters for a solar cell. So suppose this is our solar cell, typical PN junction, and this is metal contact, and at the top side also you have a contact. So light falls from this side, and then you have a circuit, and then you have a load here. So there are some parameters which we define for each solar cell, or in general for solar cells. First is the open circuit voltage. What is open circuit voltage? You just remove this load. Whatever the maximum voltage is generated by the solar cell is called as the open circuit voltage. So at this point, when you are measuring the open circuit voltage, there is no current flowing through the load, or you can say there is an infinite load. This is written as VOC. Then next is the short circuit current. This is if you just short this, you remove the load and short this circuit. So that will be the maximum current which can be drawn from the solar cell with that illumination. Illumination is constant in both the time. So but at this time the voltage will be 0 because it is short circuited. So this is the maximum current is called as the short circuit current. Then the third is fill factor. Now you see the VOC. When you are measuring VOC, you are not drawing any current. So power drawn will be 0. Similarly, when you are actually measuring the short circuit current, that is the maximum current, but the voltage is 0. So power will be 0 here also. We want to draw the power from the solar cell. So both of these points are actually having no significance to us. So if we try to follow this path with a you can say varying load, so then you will follow a path like this. So at certain point where you will have the maximum power, that point is called as the Pmax point. So suppose you have a point, this point, P1 point. So what will be the power here? Power will be the voltage, this voltage multiplied by this current. Similarly, the power at this point will be this voltage multiplied by this current. Or you can say the area under, you can say this curve. Similarly, the area of this curve or area of this, you can say curve will be giving you the power. So at the point where the power is maximum, at P max the power is maximum. So this if you divide by the maximum area, maximum possible area, this is called as the fill factor. So fill factor is the fraction of maximum power that can be extracted from the solar cell as compared to the maximum theoretical or ideal power. Ideally, what we want? We want IM or you can say ISC current at VOC voltage, but that is not possible. So we have to settle somewhere in between. So then fill factor will be, you can say it can be written by IM, VM multiplied by IM divided by VOC multiplied by ISC. And then next comes to the efficiency. Efficiency is the power, the maximum power which can be obtained from a solar cell to the input power. That is irradiated power. So it comes VOC into ISC into fill factor. VOC into ISC into fill factor will give you this area. This area divided by the power which is being illuminated on the solar cell. Suppose it is at 1.5 am and at one sun, or you can say then it will the input power will be 100 milliwatt per centimeter square, and then whatever power we are generating, so you whatever the generated power divided by the input power will give you the efficiency. A typical equivalent circuit can be drawn like this. So solar cells is basically a current source. You can consider it as a current source, and then you have a series resistance and a shunt resistance. And these are the, you can say, connections of the solar cell. So this entire circuit is the equivalent circuit for a solar cell. Now, what is the energy conversion process in the solar cells? The photovoltaic energy conversion involves four basic steps. What are those four basic steps? First thing is that light has to be absorbed. Whatever light is falling on the solar cell, it has to be absorbed by the solar cell. It is not always that 100% of the part of whatever light is falling will be absorbed. So absorption of the light in a material resulting in a transition from the ground state to excited state. Then next part is once the light is absorbed, in that after what has to be done, it has to be converted into electron and hole pairs. So conversion of excited state energy into free positive and negative charge carriers, that may be electron and holes in inorganic semiconductors, and it will be exciton, but then exciton will also be converted into electron hole pair in organic semiconductors. So first thing is the absorption of light, this absorption of light, it will create electron hole pair, but they are bound. Then this electron hole pair with it has to be separated. Then mechanism to separate positive and negative charge carriers. Once electrons and holes are separated, then this has to be once they are actually they are created, individual electron and hole pairs, this has to be separated into positive and negative charge carriers. And then the fourth step is collection of these charge carriers on electrodes. And once these have been collected on the electrodes, then these will move to the external load. So now we come to the absorption part. Let us see one by one what are the different losses. When an radiation falls on any surface, some part of this is always reflected and some part is, you can say, it enters inside the material. Entering inside material doesn't mean it will be absorbed, but it enters inside the that material. Now it will depend on the property of material whether it will be absorbed or it will be transmitted. So what part is reflected, it depends on the N0 and N1. So if N0 is 1, which is for like air, and N1 is for, suppose we have 1.5, for the N is coefficient of reflection. So suppose it is 1.5 for glass. So suppose you have glass, then certain amount of it will be reflected, and how much will be reflected you can calculate by this formula. N1 minus N0 square plus K square, and N1 plus N0 whole square plus K square, where N is refractive index of the medium and K is the attenuation coefficient of the device. So now when the incident means when light is incident on a surface, the losses may be reflection at the surface and unabsorbed light which is leaking out from this side, means the transmitted light. If it is absorbed inside the material, it is likely that it will create an electron hole pair if it is a solar cell. At least some part of this radiation will lead to the electron hole pair generation. We will see other losses also. So if it is reflected or if it is transmitted, both these are total losses. What are solutions for to minimize these losses are coating of anti-reflection material, anti-reflecting coating which is provided over this surface normally, or these are called ARC coatings, or you can texture the top surface. If the surface is flat, in place of the flat surface, you can texture the surface like this. So what happens, the light, whatever light is falling, it is, you can say, seeing more area, and the reflection will not be the the reflection can be reduced in that case. So this texturing can be done at the top surface. And then another is concentrators. Concentrators are when you have assemblies which concentrate the solar radiation to small area. So suppose your solar cell is having 1 centimeter by 1 centimeter or 1 meter by 1 meter solar cell, and then you above that you put a concentrator which will which is having a size of about, say, some 2 meter by 2 meter. So light is then concentrated. So on the solar cell of 1 meter by 1 meter, you are putting a radiation which is having which is actually of equivalent to 4 meter square area. Now, what are the parameters? One is the reflection. Now, once the light is absorbed, light enters inside the material, how much of this portion, this light will be absorbed? It depends on the band gap of the material. And next thing is, it depends on the thickness of the material. So suppose the band gap is this much, EC minus EV, the light which is having energy less than this band gap will totally be transmitted. It will not be absorbed at all. But if the energy is more than this, then it will be absorbed. So certain fraction of light which is having energy less than the band gap will definitely be transmitted through that material. And then another is the thickness. What is the thickness role is having here? So this law we always know. If mu is the absorption coefficient and T is the thickness, then this is the intensity of light. This is the maximum intensity of light which is actually falling, and this is the light which will be transmitted out of it. So we should be having a material, we should be using a material which is having a very high absorption coefficient, and thickness should be as high as possible, but we cannot have very high thickness also because of other limitations on the solar cell. So this tells us that band gap is very important for the solar cell. Whatever material we are using, we have to select the band gap so that it absorbs the maximum of the light. Some of the typical materials with their corresponding band gaps are shown in this figure. So suppose when we are using silicon, the band gap is approximately 1.1 electron volt, and which is corresponding to nearly 1100 nanometer wavelength. So when light falls on silicon, any energy which is having, or any energy which is less than 1.1 EV will be totally transmitted. However, the energy which is more than 1.1 electron volt will be absorbed. So these are different materials. So ideally what we should be having, if we have a material which is having very low band gap, in that case entire spectrum will be absorbed. But will it be useful? It will not be useful, because when you will make a p injection of such materials, what will happen? The built-in potential will be very low. So whatever charges have been generated, the charge cannot be separated because built-in potential is very low. Whatever electron hole pairs are generated inside the depletion region of a p-n junction, they need to be you can say sent out from that and sent to the electrodes. If you have very low EBE, these cannot be separated. So you will have to find an appropriate balance between band gap and the total efficiency. So for like gallium arsenide, entire spectrum above 770 will be absorbed. If we see here, we can say visible light up to, so you can say here 0.4, it constitutes nearly 44% of the total sunlight. Then this part up to 1.5, it is nearly 37% of the total energy which is falling. And in ultraviolet part, we have nearly 7%. And after this 1.5 electron volt energy, we have very, you can say, less fraction, that is nearly 11%. And above this, it's a less than 1% energy. So now we can summarize what are different loss mechanisms in the solar cells. If light is falls on a solar cell, uh, it can be reflected away. So if it is reflected away, that is total loss. And it cannot have any contribution in our electrical energy. So then suppose some part has been coupled. Now what will happen? The photon, though it has entered inside the solar cell, it may absorb or it may not absorb. So if photon is not absorbed, that is also a loss. Now suppose the photon has been absorbed, then it has to create free charges. Electron, first thing is the bound charge, then after that free charge. This bound charge is converted into free charges. Suppose these free charges are created, then these charge can recombine also. If this recombines, that is also loss. It will not lead to any electrical output. Now, so if these are not recombined, then we can separate them. So these are if these have been separated, so these will be separated. Then after the separation, these has to be collected at the electrodes. They can also combine at this stage also. So these are called as the electrical losses here. So now you have two kind of losses, optical losses and electrical losses. So contact material, as we saw earlier also, that is also important, and the metal semiconductor contact also creates a problem for the collection of charges at electrodes. There are different kind of recombinations inside a solar cell. One is the radiation recombination, radiative recombination, where the emitted light is when they combine electron and hole pair, they emit a light or photon. Then there are trap assisted also, where in between there are traps and they provide a recombination center, surface recombination and OJ recombination. And as soon as you start putting the solar cell inside radiation, the temperature of solar cell also rise. So because of that, there are other problems inside the solar cell because of this rise in temperature. So all these loss mechanisms has to be minimized for a solar cell. Now, what are the physical limits of the solar cells? First thing is that let us consider a material which is having a band gap of Eg and a photon is falling on that. If the energy of photon is exactly h nu, which is equal to the Eg, in that case what will happen? An electron hole pair will be generated and the energy of this electron hole pair will be exactly equal to the energy of this photon. But what happens when the photon is having higher energy as compared to the band gap? So in that case, the hole, or you can say, will be here, or suppose electron is hole is here, and this photon is having higher energy, then the electron will move to a higher position. But this energy, this much energy is immediately lost by the electron by thermal vibrations or by collisions, and it will come back to this point. So suppose a hole is created here, electron is created here, so within certain time, this will lose this energy thermally and it will come back here, and so this will also come back here. So this much extra energy which actually has been absorbed by the photon, by the material from the photon, but this energy will not be useful and it has gone into heat only. However, if the energy is less than the band gap, then it will totally transmit. It will not be absorbed at all. So first is spectrum loss. What is not absorbed is waste. So the band gap determines the fraction of energy that can be absorbed. So if the energy is less than band gap, it will be totally transmitted. If absorbed photon is having higher energy, then it is emitted in the form of heat and the temperature of the solar cell will increase. However, it will not give any contribution in the electrical output. Then another loss is the impedance matching. We know from our basic electronics that in order to have a efficient power transfer, there should be an impedance matching. So if the impedance is not matching, then also there will be loss. Actually, the carriers will not be extracted and they will recombine. The recombination loss, if absorption is allowed, emission is also allowed because this follow the same rules, same transition rules. So this electron hole pair, if they are not separated in time, they will actually eventually recombine. Then there is a black body radiation. If the temperature of the solar cell is not at you can say absolute zero, then it will emit certain amount of radiation. Every body emits a radiation. Uh, so this radiation at about 50 degrees centigrade, it typically 7% of the total loss. So if we summarize here all these losses, so for different band gaps, so actually this depends on the band gaps of the material. So if you have a material which is having typically 1.4 1.3 electron volt, then you can have the maximum power which is nearly 25%. So for low band gap materials, actually you have losses here. For this part is nearly for the other losses. So by if you recombine or if you can add all these losses, then the limit for your solar cells were calculated by Shockley and Quasier in their famous paper. So for like these are on x-axis you have band gap and on y-axis you have the maximum efficiency which can be obtained using that particular solar cells. So by considering all these losses which we saw in that slide, so like for silicon, suppose it is having nearly this band gap. So in ideal case, if everything is perfect, then we cannot have more than this efficiency. So that is the maximum possible efficiency which we can achieve using a silicon solar cells. These are for different solar cells. So for like indium phosphide solar cell, we can have nearly the same. But if suppose we have a solar cell which is made of the germanium material, germanium, by using germanium also we can make a solar cell similar in the same way. P-type germanium and type germanium, join them together, make a PN junction. But that will give the maximum possible efficiency 21%. Why? Because though absorption will be more than silicon, but what will happen? They will recombine, they will not be collected. And so like for amorphous silicon, we have nearly 27% maximum possible efficiency. So in order to calculate this efficiency, what we have accounted, one is spectrum loss, how much spectrum is lost, then black body radiation. When the solar cell is at a slightly higher temperature, it emits a radiation. Then recombination and impedance matching. So what are the desirable properties for a good solar cell material? For appropriate semiconducting material selection, the optimum energy band gap matching with solar energy. Ideally, we should absorb the maximum, as I have already said. So the band gap should be zero, but that is not that will not give us any uh, uh, electrical energy. So we need to have an optimum energy band. Then high absorption coefficient for low thickness cost. If absorption coefficient is high, then we can fabricate the solar cell having a lower thickness. The next is good carrier mobility. The electron hole pair which has been generated, they should be having a very high mobility. So if they are having high mobility, they can move faster inside the material before. So they are collected before the recombination. Then large carrier lifetime. Carrier lifetime is the time before they recombine. So if the carrier lifetime is larger, in that case, there is a very good probability that they will be separated and collected at the electrodes before they actually recombine. Then large built-in field for the effective charge separation. Large built-in field, which is the built-in field is actually if it is less, what will happen? The carriers will not move, or the effective force which is being put on these carriers is due to the built-in field. So more the VBI or more the built-in field, the there is a more force, and they will it is quite probable that they will move towards the electrodes. Then large diffusion length. Diffusion length is the average length before they recombine. So it should have a large diffusion length, and then small surface recombination. Why surface recombination? Because at the surface we do not have actually at the surface there is a there is a break in the continuity of the crystal. So because of this break in continuity, an extra several extra energy levels are created, and these energy levels uh, are the source of surface recombination. So we should try to do something to avoid the surface recombination. There are other considerations also. As I told in the reflection side, we have to do some anti-reflection coating so that the reflection of the radiation can be minimized. For this, one is coating of different ARCs, and then texturing the surface. Texturing the surface can also reduce the reflection losses. And then we have multi-layer coatings also. Multi-layer coatings also reduce the reflections. Then for series resistance, if we have better metallic grid design and high conductivity contacts, then series resistance of the solar cells can be reduced. For the improved transparent conducting coatings, typical N-type, we have ITO, SNO2, zinc oxide. Of P-type, we have some, you can say, materials like copper aluminum oxide or copper indium oxide, but they are not well developed. So these normally TCOs are used in the N-type side only. So based on the type of crystals used, silicon solar cells can be classified in three categories: single crystalline silicon solar cells, polycrystalline silicon solar cells, and amorphous silicon cells. Single crystalline solar cells are when a single crystalline or monocrystalline silicon cells are produced from the pure silicon single crystals. Since the monocrystalline silicon is pure and defect free, the efficiency of cells will be higher. Now let us see a typical fabrication process for a monocrystalline silicon solar cell. So this is our starting material, which is a P-type silicon. As I said, because there are not many TCOs available for P-type, so typically the surface which from where a TCO is used is opposite. So we start with the P-type silicon. So this is typical ingot, which is having this surface are like this. So first we cut it, and we cut this by some sewing machine, and so this part is removed, and we get a silicon wafer like this. Then we texture both these sides. Texturing is to increase the absorption area and reduce the reflection. So this is done by chemical etching mostly. Then phosphorus diffusion is done. So this red part is phosphorus diffusion. Then after phosphorus diffusion, what will happen? This P-type will get converted into N-type. Now this is also actually conducting, so then we cut this part from both the side, and then so as isolation takes place, now you have this is P and this is N. Then a anti-reflection coating is deposited over the top of it. Then the front contacts, which are made by printing or by thermal evaporation. Then the back contact is also done by either thermal evaporation or printing. And after this co-firing, then you can get this kind of silicon solar cell. So this is the typical fabrication process of a solar cell, starting from the different way. So you have a P-type substrate here, then you have these are the textures which we are talking about, and then every silicon a native layer over it here, but it is just then above that ARC coating is done surface. These are the actually and this is the typical JV characteristic of a solar cell, which is having area of 4 centimeters square. J means the current density, which is the current per centimeter square. We at BARC also developed solar cells. So that is space quality solar cells. These were developed in 70s. So space quality silica solar cells of nearly 10 by 20 and 20 by 20 millimeter square were developed. And for this 1 ohm per centimeter, 1 ohm centimeter P-type silicon was used. The different fabrication process steps are: the phosphorus was diffused to make zero point 0.3 micron thick n-type layer over the top surface of what p-type substrate, and backside junctions were removed by etching. The front contacts were made by titanium, palladium, and silver, 3 layers, and this was the typical thickness of these layers. And these were deposited using metal mask, thermal evaporation, and backside contacts were also of the same titanium, palladium, and silver with the same process. Anti-reflection coating on the front side was done using tantalum oxide by thermal evaporation. And these cells were cut into rectangular or square size, and the typical efficiency of these solar cells were 14.5% at that time. This is the same fabrication process I have shown in this chart. So silicon substrate, which was p-type, and this was the resistivity 1 to 10 ohm centimeter. Then substrate, this is cleaned using chemical processes. Then it was heated at 850 degrees centigrade. And then for phosphorus deposition, this process we did. That is uh, nitrogen was flown through a POCl3 tube, and then it took some of the POCl3 inside it, and then uh, this was actually you can say flown through uh, a certain pipes, and then it was passed through the this P silicon. Uh, this process for if you continue for nearly 1 hour, a PN form. Then, as I told in earlier slide also, then back contacts were made, and then top side contacts were made. Then anti-reflection coating of this, and then modules were made. So this is typical device structure. You had P-type, the thickness of N-type is small, and then backside contact, and these are the front contact, and this is the ARC. These are the some of the photographs recently taken, I think 3 years ago, and these are the photographs of the solar cells which were made in 1970s, and these some of the solar cells were actually used in the onboard satellites Bhaskar and Rohini, and this technology of solar cells were transferred to BHEL Bangalore in 1984. So this is to show how these solar cells are reliable. So the solar cells which were actually made at that time, they are still working, and they are working very well. So these values are actually from the technology transfer documents, and these are the values which we measured. We keep on measuring every year, and this is the reading of 2022. So you can see the efficiency is nearly same, it has not changed. So these are having a reliability of nearly 36 years. So the silica solar cells has a very high life. They are still working. They are radiation hard. So still, if we you can say irradiate them with a high radiation, there is no change in the parameters. The intensity, if you These solar cell, what was actually developed in 1970s. These were tested by varying input intensity and still working fine, giving proportional output between 5 milliwatt and 300 milliwatt per centimeter square inputs. We varied the temperature up to 70 degrees centigrade, and these are working very fine. So till date we use these solar cells as standard for calibration. Now we come to the polycrystalline silicon solar cells. So polycrystalline and monocrystalline, if you see the difference is it has grain boundaries. So polycrystalline is actually several small volumes which are actually single crystals, but entire mass is not a single crystal. So why do we need polycrystalline? The compositional control is less stringent, less energy intensive process. It is economical because making a single crystal is very expensive. You need big instruments, large you can say systems to grow single crystals, and it serves almost same purpose. In order to make a polycrystalline solar cell, liquid silicon is used as raw material. You have a silicon, you melt it and then pour it. So whatever material is, whatever solid is formed, this is usually in a polycrystalline silicon. The material contains various crystalline sites, hence the efficiency of this type of cell is less than monocrystalline cell. What are issues with polycrystalline? The polycrystalline material quality is poorer because of the crystalline defects and metallic impurities, and the diffusion lengths are lower as compared to the crystalline silicon. Texturing is more difficult because of the different exposed crystallographic planes. See, in like in crystalline silicon, you know which is the top plane. However, if you have a polycrystalline, see, it will be randomly oriented planes at the top side, at the top side. So texturing is not as easy because the texturing is many a times it is done by chemical etching. So different planes etches at different you can say rates. So texturing is not so straightforward in this. This is the fabrication process. So you melt the you can say silicon, and then after melting you just pour it inside a container. So slowly when it get cools, it becomes solidify, and you do not get a single crystal but with a polycrystalline mass. So for polycrystalline silicon solar cells, we need solar grade silicon material. Material is cast into rectangular blocks that are cut and polished for making solar cells. So suppose you will get this kind of see, you have this container. After this, if you remove, you will get a block. You cut this block in small wafers, and these can be polished and cut to make solar cells. The efficiency of polycrystalline solar cell is low as compared to crystalline. These are typically 13 to 15%, and these are the photograph. You can make out the difference between the monocrystalline solar cell, which is which looks like this, and with a polycrystalline silicon, which looks like this. The typical efficiency for monocrystalline is 25 to 26% in ideal cases, on for the experimental device, not the commercial panels. And for a polycrystalline in laboratory, one can achieve maximum up to 20 to 23%. But typically, the panels which are available are nearly 12 to 14%. For monocrystalline case, they are up to 18 to 20% efficiency. Now we come to the thin film solar cells, second generation, which are see both these like polycrystalline silicon solar cells or monocrystalline solar cells are you are having wafer. The size of the wafer is quite big. So sometimes in also. But that require a lot of material. So then we came to the second generation solar cells, which are thin film based solar cells. Why these are important? Because the material quantity is reduced. You need a very, you can say, a very thin layer. And so obviously, if the thickness is reduced, the material is less material is used inside for the fabrication of solar cell, and it reduces the fabrication cost, and it has tunable material properties because now you are not having a 3D structure. So you have a you can say very thin layer on the top, and so the material properties can be tuned. What are different important thin film solar cells? Amorphous silicon solar cell, cadmium telluride solar cell, and copper indium gallium diselenide solar cells. CIGS, CDTE, and amorphous silicon. Amorphous silicon is different than the polycrystalline silicon, which we saw yesterday. Amorphous silicon is a thin film solar cell. So if we try to just see the difference between monocrystalline and amorphous, so monocrystalline or single crystal is a material where the long range order is followed, means it is all the atoms are at the perfect lattice point. However, in amorphous, there is actually no order. Ideally, for an amorphous material, there is absolutely zero order. So you will see every atom is seeing a different surrounding, if you can see. And there are some dangling bonds also. Suppose this silicon is there, it has actually three bonds are with silicon, but one bond is unsaturated. So usually this is done by this is compensated by hydrogenation. So as we already know that absorption is very important for solar cells. So for different solar cells, if we have silicon, crystalline silicon, nearly 1.1 EV or more, the entire, you can say, spectrum is absorbed of that energy. And the band gap of like amorphous silicon is this here, and typical absorption coefficient for this material at different photon energy are plotted here. So suppose for like amorphous silicon, if we see the absorption coefficient in these energies, which are more than 1.5 ev, are higher as compared to the crystalline silicon. Or like for copper indium selenide, the absorption coefficient is very, very high in the entire range. So a very thin layer of CIGS is can actually absorb quite a reasonable amount of the incident radiation. However, for silicon, if you want to use a thin film of silicon, then you are having nearly 2 order less of the absorption coefficient. So you need at a thickness of at least 100 times more than the CIGS. However, in the silicon also, the amorphous silicon, though it is actually just one order more than silicon, more than crystalline silicon. So if you are using about 0.3 mm of the crystalline silicon wafer, then the same amount of energy can be, same amount of radiation can be absorbed in 0.03 mm of the silicon. So you can have a very thin layer of this material, and it can serve the same purpose. Similarly, for the gallium arsenide, you can also use this as a in like you in thin film also see above 1 point nearly this energy the absorption coefficient is nearly 10 to the power. So amorphous silicon is obtained by depositing silicon film on the substrate like glass plates. So it is deposited on substrate. Deposition done by sputtering, glow discharge or vacuum deposition process. It has a higher optical gap, which is nearly 1.8 electron volt, while in the case of silicon it was nearly 1.1, and much higher absorption coefficient, nearly 100 times, as we saw in the earlier slide, than crystalline silicon. 1 micron thickness is sufficient. How much is 1 micron is you can see our hair is approximately 75 microns. So even nearly 100 times less to that the thickness of our hair. You require that much only thick layer to absorb. See, dangling bond can be reduced by hydrogen doping in amorphous silicon. So the as we saw in like earlier slides, there are some bonds which causes problems because so these bonds are saturated by hydrogen treatment, by hydrogenation. So at those particular points, a hydrogen atom is attached. So then it becomes hydrogenated silicon. Lower carrier lifetime and mobility in comparison of crystalline silicon. As a result, the efficiency of amorphous cell is much lower than that of the other two types. These are used mainly in low power equipments such as watches and pocket calculators, etc. In all the like in calculators, if you see there is a small solar cells at the top of it. Those are the amorphous silicon solar cells developed on the base of thin film technology. So amorphous silicon, as I said, so you are having like suppose this is structure, you are having many dangling bonds here. These dangling bonds are all saturated by hydrogen by a process hydrogenation. So a typical amorphous silicon solar cell structure is like this. You have a glass surface, glass top, and over that you have a transparent conducting oxide. What is transparent conducting oxide? It is an oxide material which is actually conducting, but at the same time transparent also. Then a P layer of this amorphous silicon is deposited. Then we deposit pure silicon layer of slightly, or you can say this high thickness. Then we deposit a layer of N amorphous silicon, and then there is a bottom metal contact. So light falls from this side, and the contacts are made between this TCO and this metal contact. So this is typical working. photon falls and electron and hole pair is generated, and because of this there is a p-type and n-type material, so a built-in potential is generated. And then what happens, this electron, it travels this side and holes it travel this side, and there are ohmic contacts made using TCO and metal, and these are collected and the current flows through the circuit. So you have if you want to compare between monocrystalline, polycrystalline and amorphous silicons. So in monocrystalline, the crystalline order is single crystal, and in polycrystalline it is tiny small crystals, and in amorphous there is no crystalline order. The typical thickness is 50 to 300 micron for monocrystalline silicon. For polycrystalline silicon, the thickness is same as of the monocrystalline, and typical efficiency are 25 to 26%, for this 20 to 23%, and for a amorphous silicon it is less than 1 micron, and the efficiency is nearly 7 to 13%. Now we come to another thin film, which is copper indium gallium diselenide solar cell. This is the based on cadmium sulfide CIGS. One is CDS and another is CIGS material. So it has better. I am not feeling well. So these are like based on CDS, CIGS. So you have this kind of structure, glass over glass, then you have a back contact here of let us consider for molybdenum, which is having nearly 0.5 micron thickness. Then p-type light absorber, which is CIGS. This is p-type material, so it is having nearly 2 micron or slightly more than that. This is the thickness of CIGS. Then over that, the N layer of CDS is deposited, which is very thin, of nearly 0.05 micron, and above that you have a zinc oxide layer, which is actually transparent but the conducting oxide. And then above that you have these electrodes which collects the current. So the heterojunction between p type of CIS or copper, indium gallium selenide and CDS prepared by co-evaporation process. The efficiency of these solar cells are up to 20%. The band gap of CIGS is graded by suitable composition profile of indium and gallium by changing the ratio of like this indium and gallium, we can tune the band gap. ITO and ZNO are used as the conducting and transparent conducting films. So these are at the top side, either you use ITO, indium tin oxide, or we use zinc oxide. Then another solar cell, which is CDT solar cell thin film, in which if you see these are two layers, cadmium sulfide and cadmium telluride. So these are having a high optical absorption. The band gap, typical band gap is between 1.45 to 1.5 electron volt. CDCl2 treatment is required to avoid interdiffusion between cadmium sulfide and CDT layers. The typical efficiency of this kind of solar cells is 21%. And because cadmium is very toxic, so these solar cells are not very common in in normal day-to-day uses, but uh, because the efficiency is quite high, these solar cells are used in the space applications many times. So if we see typical layers, so we have here at the top side we have glass, and then below glass you have just below glass you have anti-reflection coating, and then you have you will be having a layer which is of N type, which is of this is the layer of N type CDS, and then there is an intrinsic layer, this layer of cadmium telluride, and then you have P type layer of zinc telluride. So now the structure becomes like you have P intrinsic and then N, and this is the top side, and this is then you have a back contact here. So between these two you make connections. Then there are elements, third group elements and fifth group element. So solar cell based on these semiconductors are very important because the band gap of gallium arsenide, gallium aluminum arsenide, and gallium indium aluminum phosphide materials can be easily varied by composition. If you keep on changing the composition, the uh, band gap can be varied. If band gap is varied, accordingly the absorption of the incident radiation can be enhanced. So best solar cells prepared by metal, organic, chemical vapor deposition or molecular beam epitaxy. These kind of solar cells, because they are very, very thin films. So these are deposited by MOCVD or MBE. Multiple junction to achieve higher efficiencies. You have several solar cells deposited over one solar cell. Means there are several solar cells deposited one over other. So then by doing this, you can actually enhance the efficiencies. And in different cells, different spectrum of the radiation is absorbed. So by this way, actually you can enhance, you can go up to efficiency of more than 40%. Actually, the best efficiency in multi-junction solar cells is more than 45%. And even for the reported values for these are gallium arsenide based solar cells. The single junction, on the other hand, the single junction may have the maximum efficiency of 27%. These cells are highly reliable and radiation resistant. Due to high material and fabrication costs, these cells are mainly used for space or concentrator applications. So if we see a typical three junction solar cell, so like at the bottom of the solar cell, you have this material, germanium base, then gallium, indium gallium phosphide, and then indium gallium arsenide. So this is having a band gap of 0.65 electron volt. Now in the middle level, you are having indium gallium arsenide, indium gallium arsenide emitter, and base same, and then you have a window of these, and at the top you have indium gallium phosphide emitter, base, and so the band gap of this is nearly 1.86. Band gap of this is nearly 1.4. So what happens when light falls at the top, 1.8 up to 1.8 C 6 electron volt, the spectrum is absorbed inside this solar cell. However, the energy which is actually low than this 1.86 electron volt, it will pass through. It will be totally transmitted through this solar cell, but it will go into this. So out of that remaining energy, up to 1.4 electron volt will be absorbed in this solar cell, and then at the bottom which is germanium based, which is having a very low band gap of 0.6 eV. So whatever is left up to 0.6 electron volt will be absorbed inside this. So if we see here, say suppose this is our total solar spectrum. So the top cell, which is based on the indium phosphide, it will absorb this much part of the spectrum, and the middle, now the remaining part, this entire will be actually transmitted from this solar cell. So then this middle will absorb this portion of the spectrum, and the bottom cell will absorb this portion of the spectrum, and after 0.65 the remaining will go waste. So by doing such a thing, the we can enhance the efficiency of the solar cells by doing a using multi-junction. And when we say 400 sun, means we have used a concentrator, and uh, the spectrum, or you can say the radiation of radiation has been concentrated 400 times lesser. So suppose, so the best solar cell under this have given the efficiency of reported efficiency of nearly 43%, and that is at 400 suns. This is the picture of this one. So I think with this can end, and I'm not still feeling well, but I think so. With this, we complete this lecture. If you have any question, I'm ready to answer.
Student recommend.
Thank you. Today is very bad day actually.